Welcome back to lesson 21 about alternating series. We are going to solve these problems. There are 10 problems here, and now we will see series that are alternating. In what sense they are alternating? Instead of imagining a series of positive numbers, so A1, so the sequence is A1, A2, A3. And imagine they are all positive. Now we do the sequence is like this. Now the series is A1 plus A2 plus A3 plus AN. So this is the series of positive number. Now we introduce the idea of a sequence that is named as alternating series. When we do an alternating series, so imagine that we change the sign, we put A1, now there is a new series that is the alternating series. It will be A1 minus A2 plus A3 minus A4 and keep going. So we want to analyze these alternating series, how they behave. And we have a test, a theorem that say when an alternating series converge. Let's go to review this test, and this is the test that we are going to use to solve problems. So the test say like this: if you have one series A sub n, where all the terms are positive, which one is the alternating series? The alternating series is the series that is constructed from the initial series A1 plus A2 plus A3 plus A4, and the alternating series is the series that you change the sign here or here and keep going. Or maybe you change the sign at the beginning, minus A1 plus A2 minus A3 plus A4 minus A5. This is also an alternating series, and the theorem say if you have an alternating series and you want to test the convergence of an alternating series, either this one that I wrote or either this one that I will write, A1 minus A2 plus A3 minus A4 plus A5. If you want to check for the convergence of alternating series, there are two conditions that need to be met. The first condition is that the limit of A sub n, when n goes to infinity, the limit of A sub n, this A sub n, when s goes to infinity, should be goes to 0. And the second condition is that the A sub n plus 1, the value of the A sub n plus 1 have to be smaller than the value of A sub n. So the previous value is smaller than the following value, or the following value is smaller than the previous value. And this has to happen for all n. If these two conditions happens, you can say that the alternating series, either this one or this one, is convergent. So who is this one? This one is this one or this one? Okay, this is A1 minus A2. So the first one is positive. So should be, when n equal 1, should be a square, so it should be this one. So this one is this series, and this one is this series. And there is another theorem that say what is the error that you produce when you sum only n terms of the sum of an alternative series. And the error, the sum is s. You don't know what is s. But you can sum a sub n. For example, you can sum S5, A1 minus A2 plus A3 minus A4 plus A5. If you make the sum with your calculator, how far are you from the real answer? And what it says is that you are far from the real answer, and the error is always smaller than the following term, A5, a following term, A6. So the value of the following terms is the error. Okay, let's go to do the problem. Determine the convergence or divergence of this series. Let's go to write the series. When n equal 1 is minus 1 square. Minus 1 square is positive. So the series would be plus 1 plus 1 divided by n equal 1 is 3 minus when n equal 2 it would be negative. It would be 2 plus 1, it would be 3. 2 plus 1 here will be 3 minus 1 to the third power is minus 1. When n equal 2, it will be minus 1, 4 plus 1, 5 minus 1, 6 plus 1, 7. So this series look like part of it look like the harmonic series, but it's not the harmonic because it's the alternated harmonic series. And the alternative harmonic series is convergent. Why? Because first of all, the limit of a sub n, the limit when n goes to infinity of a sub n goes to 0, because it's the limit when n goes to infinity of 1 divided by n, and this goes to 0. And the second condition that have to be met is that a sub n plus 1 have to be smaller than the a sub n. So have to be smaller as the series progress, the terms are becoming smaller and smaller. So the series, the harmonic series is 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth. So the terms are becoming smaller and smaller. Then I can say, because the two conditions are met, the series, the alternative series converge. So these two conditions are applied for the alternative series. So the harmonic alternative series converge. And we have used the theorem to say that this one will converge. Let's go to the next one. Determine the convergence or divergence of this series. Minus 1 to the n, 5, n plus 1. Okay, we need to see if two conditions are met. Let's go to write first a few terms. So this starts at 1. So it will be minus 1, 5 squared, plus 1, 5 cubed, minus 1, 5, 4, plus 1, 5, 5. So this is the alternative series. And the series where it comes, this series is 1 5 squared plus 1 5 cubed plus 1 5 4 plus 1 5 5, etc., etc. So the a's are here. So I want to prove first that two conditions are going to meet. For the alternative series, I'm checking the alternative series. The first condition is that the limit when n goes to infinity of a sub n will go to 0. So this is the limit when n, this is 1 divided by 5 to the n, so it's the limit when n goes to infinity of 1 divided by 5 to the n. When n goes to infinity, 5 to the n goes to infinity, and now 1 divided by infinity goes to 0. So the first condition is met. The second condition is that a sub n plus 1 is smaller than a sub n. So as I progress in the series, this term is smaller than this term. This term is smaller than this term. And this term is smaller than this term. So it's true that a sub n plus 1 is less than a sub n. If you want to prove it, you put here 1 divided by 5 n plus 1 is smaller than 1 divided by 5 to the n. If this is true, it means that 5 to the n is smaller than 5 to the n plus 1. I multiply this by this, so the 5 to the n plus 1 will appear here. So 5 to the n plus 1 is bigger than 5 to the n? Yes, it's bigger. Of course, that 5 squared is 25. 25 is smaller than 5 cubed. Of course, so as I progress in the series, the term becomes smaller. So the two conditions are met. So the alternative series, this one, will converge. That's all. Now let's go to do this problem. Let's say determine the convergence or the divergence of the series minus 1 n plus 1 divided by n factorial. Let's go to do the absolute value of this series. This is the series summation from n equal 1, summation from n equal 1 to infinity of what? Of 1 divided by n factorial. So it will be 1 divided by 1 plus 1 divided by 2 factorial plus 1 divided by 3 factorial plus 1 divided by 4 factorial, etc., etc., etc. Oh, what will be the sum? Anyone can remember what would be the sum? I remember that e to the x is 1 plus 1 divided by 1 factorial by x plus 1 divided by 2 factorial by x squared plus 1 divided by 3 factorial by x cubed. So I remember that if x is equal 1, e to the 1 will be 1 plus 1 divided by 1 factorial plus 1 divided by 2 factorial. If x equal 1, 1 squared will be 1. 1 cubed will be 1. So this part that appears here is 1 plus 1. So this sum, this infinity sum, it will be e minus 1. E minus 1 is clear. Okay, so now we have the alternative series. The alternative series is minus 1 n plus 1. This series starts at n equal 1. So this is positive, the numerator. So it will be plus 1. The alternative series will be plus 1 divided by 1 factorial minus 1 divided by 2 factorial plus 1 divided by 3 factorial minus 1 divided by 4 factorial. So now we have to ask ourselves, is this series converge or diverge? So this is an alternative series. When it will converge? It will converge when the limit, when n goes to infinity of a sub n, or the limit when n goes to infinity of 1 divided by n factorial goes to 0. When n goes to infinity, this is the limit, when n goes to infinity of 1 divided by n minus 1 by n minus 2 by n minus 3, etc. When n goes to infinity, 1 divided by n goes to 0. 1 divided by n minus 1 goes to 0. Sorry, when n goes to infinity, yes, 1 divided by n goes to 0, 1 divided by n minus 1 goes to 0, so it's the product of many zeros, so it will be 0. So if the first condition is met, the limit when a sub n goes to 0, when n goes to infinity, it will be 0. And the second condition is that a sub n plus 1 have to be smaller at a sub n. As I advance it, the next term is smaller. So the question here is 1 divided by n plus 1 factorial is smaller than 1 divided by n factorial? Oh, to know this, we will do this n factorial. What it means is n factorial is smaller than n plus 1 factorial. Oh, it's true. It's true because n factorial is n by n minus 1 and keep going. And this is smaller than n plus 1 factorial means n plus 1 plus n multiplied by n minus 1. So on the right side of the equation, I have the same that in the left side, but I have now an n plus 1. So a sub n plus 1, so this inequality is true because the right side is always bigger than the left side. So n factorial is bigger, is smaller than n plus 1 factorial, or 1 divided by n plus 1 factorial is smaller than 1 divided by n, or a sub n plus 1 is smaller than a sub n. Because the two conditions are met, I can say the alternative series, 1 divided by 1 factorial minus 1 divided by 2 factorial plus 1 divided by 3 factorial minus 1 divided by 4 factorial converge. Of course, that the series of the absolute value, this one, also converge. And converge to e minus 1. I did it somewhere. Converge to e minus 1. Where did I did that? Oh, I imagine that I did it. Wow. I was sure that I did it. Okay. Okay. So what I said is that e minus 1, yes, I said here that all these terms are here, so this should be e minus 1. E minus 1 should be all this. Okay, so when this happens, when the alternative series converge, and the series, this one, and the series converge, we say that there is absolutely convergence. And why is important absolutely convergence? Because sometimes you can manipulate the alternative series to make sums, and you have to, it's a tricky thing. You can find, you need absolute convergence to make sure that you can manipulate series, like summing series, summing a sub n with b sub n, summing a sub n plus b sub n. You'll better have a sub n and b sub n a convergent series to make the sum. You will be safe. Summing infinity series have surprise. Okay, let's go to do this other. Determine whether the series minus 1 to the n divided by n factorial converges conditionally or absolutely. Well, it converges absolutely. I said that because the series of the absolute value converge and the alternative series converge. So it converges absolutely. So let's go to write the series. One plus 1 divided by 2 factorial. I don't know, plus 1 divided by 3 factorial. Let me do it right. When n equal 1 is minus 1. Minus 1. Okay. But I'm going to do the absolute value. So plus 1 divided by 4 factorial plus 1 divided by 5 factorial. This series converge. How I know that it will converge? Because I know that it converges to e minus 1, I said. So this series converge. The alternatives, alternative test, the alternative series we have seen in the previous example, the alternative series minus 1 plus 1 divided by 2 factorial plus 1 divided by 3 factorial minus 1 divided by 4 factorial plus 1 divided by 5 factorial. The alternative series converge. So, the alternative series converge. The series of the absolute value converge. So we say that we have absolutely converges. It converges absolutely. So it converges absolutely. Which one converges absolutely? Well, the alternative series, this one, converges absolutely. Why? Because the series of the absolute value converge. Okay, let's go to the next. Determine whether the series minus 1 to the n plus 1 n divided by natural log converges conditionally or absolutely or maybe diverge. So let's go to write a few terms of the series. Let's go to write the terms of the absolute value of this series. It will be 1 divided by 1. 1 divided by 1, it starts 1 divided by 2 by natural log of 2, plus 1 divided by 3 by natural log of 3, plus 1 divided by 4 by natural log of 4. Natural log of 2 is positive. Natural log of 3 is positive. Natural log of 4 is positive. So the series is of positive numbers, as the theorem is asking us. This is the series of the absolute value, and the integral test will say that this series converge. This was done on the lesson, on the previous lesson about the integral test. So the series summation from n equal to infinity of 1 divided by n natural log of n diverge. Now let's go to study the convergence of the alternative series. The alternative series is when n equal 2 is positive. When n equal 2 here is 3, is negative. So it's minus 1 divided n equal to 2 natural log of 2 plus 1 divided by 3 natural log of 3 minus 1 divided by 4 natural log of 4 plus 1 divided by 5 natural log of 5. Is this an alternative series? Yes, negative, positive, negative, positive. It's an alternative series. It converges. Two conditions have to be met. The first condition is the limit when n goes to infinity of a sub n, or the limit when n goes to infinity of 1 divided by n natural log of n will have to go to 0. And yes, this goes to, when n goes to infinity, this n goes to infinity, natural log of n goes to infinity, 1 divided by infinity goes to 0. So for sure this limit will go to 0. The other condition that we have to meet for uh, an alternative series to convert. This is the first condition. The second condition is that the term of the series has to be smaller. As I progress in the series, have to be smaller. So this term have to be smaller than this one. This one have to be smaller than this one. So the question is 1 divided by n plus 1 natural log of n is smaller than 1 divided by n natural log of n? Or how we will solve this? So if we multiply here, we have n natural log of n have to be smaller than n plus 1 natural log of n. Natural log of n plus 1. Sorry. Natural log of n plus 1. Is this in the right side greater than this? Of course that is greater. But because here I have an n, here I have a big number, n plus 1. Here I have natural log of n, but the natural log of n is a increasing function, so the natural log of n plus 1 is even bigger. So it's true that this product is bigger than this product. So the two conditions are met. For a sequence, for an alternative sequence to convert, the limit of a sub n goes to 0, and a sub n plus 1 is smaller than a sub n. So this series, the alternative series, converge. But the series of the absolute value do not converge, they diverge. So the convergence of this alternative series will say that is conditionally converges. It converge, this series converge, but converge conditionally because the series of the absolute value diverge. So the series converge conditionally. Let's go to the next problem. Okay, now let's go to determine whether the series minus 1 to the n multiplied by n divided by n cubed minus 5 converge conditionally or absolutely converges or diverge. So let's go to write a few terms of the series. Let's go to write first the absolute value of the series. The absolute value from n equals 3 to infinity of n divided by n cubed minus 5. This is equal, when n equals 3, is 3 divided by 3 cubed minus 5. When n equals 4, is 4 divided by 4 cubed minus 5. When n equals 5, is 5 divided by 5 cubed minus 5. This is the series of the absolute value. And the alternative series, when n equals 2, is positive. So it's plus 3 divided by 3 cubed minus 5 minus 4 divided by 4 cubed minus 5 plus 5 divided by 5 cubed minus 5, and keep going. 6 divided by 6 cubed minus 5. Okay, is this series converge? So the alternative series converge or diverge? The alternative series, to converge, two things have to be met. When the limits, when n goes to infinity of a sub n, have to go to 0. And a sub n plus 1 have to be smaller than a sub n. Let's go to see if the two conditions are met. The first condition are met because the limit when n goes to infinity of n divided by n cubed divided by n cubed divided by n cubed minus 5 divided by n cubed, if I divide this, is 1 divided by 1 minus 0. So this is 1, this limit is not 0. Oh, let me see, is n divided by n cubed is 1 divided by n squared, sorry. So it's 1 divided by n squared, this is 1 divided by n squared, this is n cubed, this is 1, and this is 0 when the limit goes to n to infinity. The numerator goes to 0, 0 divided by 1 is 0, so the limit is 0. Okay. And the second condition is a sub n plus 1 is smaller than a sub n. A sub n plus 1 is n plus 1 divided by n plus 1 cube minus 5. Is this smaller? We don't know. Is this smaller than n divided by n cube minus 5? Well, to know if this is smaller, we do exactly the same thing. If this is smaller, we don't know. If this is smaller, this thing has to happen. N cubed minus 5 multiplied by n plus 1 have to be smaller than n that multiply an n plus 1 cubed minus 5. Okay, we can work here and we can write this like this. N4. So if you do a little bit of algebra, it's not very difficult, you will prove that this is true. You develop here, you multiply here, and you will see that always the right side of the equation is bigger than the left side of the equation. So as a conclusion, we will say that the alternative series converge. The alternative series converge. And what is the alternative series? The alternative series is the series that does plus 3 divide this one. This one is the alternative series. Now, this one is the alternative series. Where is the alternative series? I didn't write it. This one, minus, plus, minus. And this is the absolute value of the series. So this one converge or diverge? We have to study this one. Is the summation from n equal 3 of n divided by n cubed minus 5. Let's go to do this one. So the alternative series we said converge. Now the other one is n divided by n cubed minus 5. So this series converge or diverge. If this converge, we will say because the alternative series converge, if this one also converge, we will say that this series, the alternative series, converge absolutely. If not, we will say it converge, the alternative series converge, how you say, not absolutely, conditionally. Okay. So let's go to see if this converge or doesn't converge. So this, to know if this converge, I see here n divided by n cubed, I see 1 divided by n squared, so I will do the limit comparison test. The limit comparison test, I do the limit when n goes to infinity of a sub n, and compare with 1 divided by n squared, and see if it's a finite number. Is this a finite number because we already know that this one converge, this one will converge. Let's go to try if this is true. If this is true, we found that this converge. So the limit when s goes to infinity of this expression is n divided by n cubed minus 5 multiplied by n squared divided by 1 is n cubed divided by n cubed minus 5. If we divide numerator and denominator by n cubed, we will have n cubed divided by n cubed divided by n cubed divided by n cubed minus 5 divided by n cubed. When s goes to infinity, the limit when s goes to infinity, it will be equal to 1 minus 0. This will go to 0. So the limit will be 1, so it's a finite limit. So because it's a finite limit, what it's saying the comparison test, is that this converge, then this converge because the limit is a finite limit. So we know that the alternative series converge. And the absolute value of the series also converge. So the convergence is absolutely. It converges absolutely. So the alternative series converge. And how it converge? Absolutely, because the one with the absolute value, absolutely, because the one with the absolute value also converges. If not, if the one with the absolute value diverge, we will say that the alternative series converge conditionally. Converge, but conditionally. Conditionally meaning that the series with the absolute value diverge. Okay. Now the following problem say determine whether the series minus 1 to the n r tangent of n converge conditionally or absolutely or diverge. Okay. What happened with this series? Let's go to see the absolute value of the series. The absolute value of the series is the summation from n equal 1 to infinity of r tangent of n. So let's go to put a few numbers, r tangent of 1 plus r tangent of 2 plus r tangent of 3. Do you see that this series converge or diverge? Well, if you represent the function r tangent, that is this one, is asymptotic with minus pi divided by 2, and pi divided by 2 is asymptotic at pi divided by 2. So r tangent of 1 is here 1 radians, so it's this amount, this height. R tangent of 2 is this height. R tangent of 3 is this height. The sum of all when n goes to infinity. It will be converge or diverge. It will diverge because every time the a sub n, for using the divergence test, the limit when n goes to infinity of a sub n is different than 0. So the series diverge. So it's clear that the series diverge, the series of the absolute value. So now we have to go to the series to the alternative series. What is the alternative series? R tangent of 1 minus r tangent of 2 plus r tangent of 3 minus r tangent of 4, etc., etc. Does this series converge? To converge, the limit when n goes to infinity of a sub n have to be 0, but it doesn't be 0. Also, the term a sub n plus 1 should be smaller than a sub n, but it's not true. It's not true. Any of the conditions are met because r tangent of 1 is the r tangent of 2 should be smaller than r tangent of 1, but it's not this what is happening. R tangent of 3 have to be smaller than r tangent of 2, but this is not what is happening. So the alternative series diverge. So what happened here? Here what is happening is first the alternative series diverge. The alternative series diverge. The series with absolute value, the series with absolute value, the series r tangent of 1 plus r tangent of 2 plus r tangent of 3 diverge. So as a conclusion, there is nothing like conditional convergence or absolutely converges. So what we would say is the series diverge. The series diverge, meaning that diverge the alternative series and also the series of the absolute value. So the problem is done. Let's go to this one. So now we do the next one. The next one say the series sine of n divided by n squared and is an alternative series. Okay, sine of n divided by n squared. Let's go to do a few terms. Summation. N start at 1. So it will be sine of 1 divided by 1 squared plus sine of 2 divided by 2 squared plus sine of 3 divided by 3 squared. Is this an alternating series? Well, sine of 1 is sine of something like 56 degrees because it's 1 radian. And this is positive. Sine of 56 is positive. Sine of 2 is the sine of 2 radians. 2 radians is like 110 or 156, 50 by 50 is 100, 112. More or less, divide by 4. Okay, sine of 112 is also positive, so this is not an alternative series. Sine of 3 is sine of 57, is sine of 160 degrees, also positive. It becomes negative with sine of 4 divide. Sine of 4 radians is negative, but this is not an alternative series in the sense that the sign is not changing. Plus, positive, negative, positive, negative. This is not what is happening. So the series is not an alternative series. So determine whether the series converge conditionally or absolutely or diverge. So how we can answer this question? From one side, the series is not an alternated series, so we cannot use the theorem for alternated series to see the convergence of the alternative series. We cannot see if you remember that the two conditions have to be met for an alternative series. That is, the limit of a sub n goes to 0 and a sub n plus 1 have to be smaller than a sub n. Here, the series is not an alternated series. How we can deal with this? How we can extract information from here? What we will do is the following thing. We will analyze the series of the absolute value. So we'll analyze the summation from 1 of sine of n divided by n squared in absolute value. So we analyze sine of 1 divided by 1 squared plus sine of 2 divided by 2 squared plus sine of 3 divided by 3 squared. From the moment to put the absolute value have no effect because sine of 1 is positive, sine of 2 is positive, sine of 3 is positive, but sine of 4 is not positive. So now it have sine of 4, it have something different in the series. Now I am creating a series of all positive numbers, A1, A2, A3. So these are sine of 5, with this sine of 5 is negative, but with the absolute value will be positive. Now the question is, if I want to extract information about this series, the question that I will wonder is this series convergent? And I will create a new theorem. The new theorem will say, if the series of absolute value converge, then the series converge. Wow! It means if this series converge, then this one, sine of 4 divided by 4 squared plus sine of 5 divided by 5 squared, the one that is not an alternative series converge. So now the question is, how can I prove that this series, the absolute value of the series, is converge? If I prove that this series is converge, my theorem says that if the series of the absolute value converge, then the series converge. This one will converge. But the question is how I can prove this series is converge. Well, to prove this, we will use a theorem, the comparison test. We will compare the series sine n, sine absolute value of sine n divided by n squared. This is always equal, less or equal, sine of n, the maximum value that can take is between 1 and minus 1. And the absolute value of minus 1, if it takes the value minus 1, is 1. So sine of n divided by n squared is smaller than 1 divided by n squared. So what I will do, I will use the comparison test of this series, the one with the absolute value, and I will compare with 1 divided by n squared. And I will say sine of n divided by n squared, this is smaller than 1 divided by n squared. But this series, the summation, this one converge. And this other one is smaller than one that converge. So then it converge. Then this one also converge. And now I will use my theorem. If the series that of the absolute value converge, then if the series of absolute value converge, then the series converge. So this one will converge. So what it say here, some of the terms positive or negative, well, to understand what it says, not so easy, but this is it. This is the reason. Okay, let's go to the next problem. Problem 9 say it can be shown that the summation minus 120 plus 1 divided by n minus 1 factorial is 1 divided by e. Use the fourth partial sum to approximate 1 divided by e and use the remainder theorem to estimate the error. Okay, so let's go to analyze what it says. It says that the summation, it says e to the x, so let's go to see what it says. It says e to the x is 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the n divided by n factorial. So e minus 1 is 1 minus 1 plus 1 divided by 2 factorial minus 1 divided by 3 factorial plus 1 divided by 4 factorial, etc. It's an alternative series. So e minus 1, which is 1 divided by e, is this series. So use the four partial sum to approximate 1 divided by e. So the four partial sum is here. 1 minus 1 is 0, so it's 1 divided by 2 factorial plus 1 divided by 3 factorial. So I can approximate, this is an alternative series, and what I'm saying that is 1 divided by e is approximate. If I take the four the four terms, only four terms, is 1 minus 1 is 0, and 1 half minus 1 6 is 1/3. So 1 to the a, 1 to the e is 1/3. Is 1/3. Is approximately 1/3, or is approximately 0.33. What it says that 1 divided by 2.7 is 0.33. Whoa. Yes, but there is an error. What is the error? The error is smaller. The error we take 4 times. The error 4 is smaller than the term a sub n plus 1. The absolute value of the error, of course, but here is positive, so the absolute value of the error. So what is an plus 1? So it is 1 divided by 5 factorial. So 1 divided by 5 factorial is the error. So the value of 1 divided by e is approximately 0.33 or 1/3. Let's go to put 1/3. 1/3 plus minus an error. 1/3 plus minus plus an error. And what is the error? The error is a sub n plus 1. What is a sub n plus 1? Is 1 divided by 4 factorial. What is 1 divided by 4 factorial? Is 1 divided by 4 by 3 by 2. 3 by 2, 6. 6 by 4, 24, plus minus 124. So the error is 124. So you know that 1 divided by e is approximately 1/3 or is exactly 1/3 with an error, with an error of 1 divided by 24. So the difference between the real value with the real value 1 divided by e is the real value, and the sum of the fourth terms of the first 4 terms is this error. So it's a quite good approximation of the value of 1 divided by e. You can see the value of 124 is 0.041, so the error is here. The error is the value of the 1 divided by e minus the sum is the error. This is the error in absolute value. Okay. Now let's go to solve problem 10. Problem 10 say, is the following statement true or false? It say, if the summation of a sub n diverge, then the series of the absolute value also diverge. True, it say, if the series converge. You think, how you will negate this? This is true. This is true. We said if the series of the absolute value converge, then the series converge. This is problem 8. This is true. But what is asking is if this is true. If the series summation of a sub n diverge, the summation of the absolute value also diverge. This is also true because this is the negation of this. We have finished. I see you on the next lesson.